All right, so yesterday we finished up talking about preparation of diazo compounds, and we proposed a synthesis of this one below. We're almost done with the amines chapter. That means you guys should be working or getting very close to completing your sapling problems. We're going to continue on to carbohydrates today. But before we do, we're going to talk a little bit about nitrogen heterocycles. There's a few main types that I do want you guys to know the names of. Some of them you're familiar with already. What's this heterocycle? Pyridine. What does a heterocycle even mean? Let's go back to that term. Yeah, it means it has a non-carbon atom in there, right? So in this case, nitrogen's replacing one of the carbons on benzene. What about this guy? What was that? Pyrrole. So is pyrrole aromatic? So is pyrrole aromatic? Yes. In this case, this lone pair can be localized to the ring. So this is sp2 hybridized. We've got two other pairs of electrons, so 6 total electrons. What about pyridine? Is that aromatic? Yes. Yes, because in this case, the lone pair is not conjugated. It's isolated in an sp2 orbital. It's not in a p orbital. All right, there's a couple other offshoots of these too. Oh man, let me fix this.
What was the number again? Oh, factors of 4, right?
4n plus 2.
4n plus 2.
Let's see. All right, we can get into dozens and dozens of different nitrogen-containing heterocycles. This one is particularly important. It's imidazole. And then the other one that you'll often see let me clean this up. Is this guy, which is pyrimidine. All right, so let's take a look at some imidazole examples. The classic one, many of you guys are facing due to the springtime. And what was that, Stacy?
Histamine.
Histamine, right? So histamine is involved in a lot of allergic responses. And it's got an imidazole substituent coming off of it. Pyrimidines are also very important. What are they included in? What's that? Yeah, nucleotides. So we've got a lot of pyrimidine nucleotides. So let's just take one, for example. Let's see. We've got a carbonyl over here. Double bond there, lone pair, lone pair. This is cytosine. Oop, that's supposed to be an S. And this is in both DNA and RNA. This could be an exam question for next year. Is this aromatic? This is actually a tough problem. If we look at this lone pair, can it be involved in a p orbital? No, because that p orbital is already occupied, right? So this one's excluded. But we've got 2, 4. This one could be in a p orbital. That's 6. And then we've got an sp2 orbital over here. So in this case, this can actually be considered aromatic. The pyrimidine bases are all considered aromatic. It's actually how we sequence a lot of DNA is we actually use the fluorescence of these aromatic molecules in order to trace where they are in a DNA sequence. They do have some unique reactivity, and I wanted to address this really quick, but most of it's intuitive. So let's say we have pyrrole, and we react this with bromine. In this case, you actually don't need a catalyst. This will just do electrophilic aromatic substitution on its own. The question is, which position will it attack? Nope. That's electrophilic aromatic substitution. I'm giving you a hint there. It's got to be one of the top two, but then we've got to ask ourselves, is it going to put a bromine there?
Literally the top two.
Or is it going to put a bromine up here? I want you guys to try to problem solve which one is going to be the most likely position.
The right one.
Did Brian already cover it?
So if you think about it, you can draw these, and you could say, all right, if it's going to be this one, that means that, let's actually draw out the options. We could draw this attacking, kick off our leaving group. Nope. Or we could have our bromine up here and our carbocation down here. Which one do you think is going to be the most stable intermediate? So this is actually an interesting problem. So you could have a resonance structure there with a lone pair, or you could have a resonance structure with that positive charge over there. Or for this one, you could have these two. So on first glance, you would say the one on the right's the more stable one, right? But if you draw out all of the resonance structures, this one is more stable, which means that it's going to be the preferred intermediate, which means that this is going to be your only product. And this one's not observed. So if you are working with heterocyclic compounds, you do want to actually go through, draw out all of the possible resonance structures. It's not as easy as just saying it's going to be an ortho paradirector or metadirector. You have to actually draw out all of the resonance structures and problem solve your way through it. Yep?
If this problem is in the ACS, how do we just look at it? Is there a drawing?
I would go through your practice workbook, but typically they don't have problems as challenging as this on there. They will have ortho-meta or ortho-para versus meta-directors, but usually they don't have much with heterocyclic aromatic compounds. Yeah. All right, we could do the same thing too with pyridine. If we want to do this with pyridine, we actually have to crank up the heat really, really hot. But you can brominate pyridine. And in this case, using the same sort of logic as before, you're going to brominate your pyridine going through the more stable carbocation. You want to make sure that breaking aromaticity is as favorable as possible by having as much resonance delocalization. You won't observe bromination occurring in the 2 position on the pyridine. There are other ways to make those compounds, but we're really not going to get into those for this class. So if you do want a challenge to work on at home, you can try to go through and draw all the resonance structures for these, just like we did with parole, if you are kind of struggling with this concept. Does that make sense? Yeah, it's just a lot of going back to old chemistry. All right, so at the end of the amines chapter, what I have is the reaction summary. I didn't print it out for you guys this time, just to try to save some paper. If you do want copies, you're more than welcome to come by my office and I'll print you out some. But these are the main reactions you should know. So for the next exam, a lot of these will be on here. It was kind of frustrating on the last exam because I literally took reactions off of the reaction summary and people were missing them. So for example, reducing a nitrile was on the last exam. And in this case, you can reduce it to a single bond. You should know how to interconvert between all of these amines. Some of these reactions are already reviewed from what we know. For example, converting between nitrobenzene and aniline, and then doing simple substitution reactions. There are with some new ones. The Gabriel synthesis was new. That wasn't on the last exam, but it could be on this next one. We saw reductive amination already. And then the new reactions that we've seen were acylation, and then reactions with diazonium salts, so all the Sandmeyer variations, and then the azocoupling reaction. I wouldn't be surprised if there is an azocoupling type reaction on there, so you should try to study up on all the diazonium salt stuff. Are there any questions on chapter 23 as far as the exam goes? No?
I feel like there were, like, looking in the book and in the notes, there weren't many mechanisms.
No, because a lot of the reactions are very similar to what we've seen before. So the Gabriel synthesis is new, and the formation of azodies is
Well, the NA,
what's new?
the one that one, the one on the right, the NADH3CN.
Mm-hmm.
I didn't see a synthesis for the last part, or for mechanism for the last part when you do the NADH3CN.
Yeah, that's a good question. So with a hydride source, you can always think of these as H-.
Oh.
So you're just delivering a hydride to the molecule. In this case, it's a very gentle source of hydride. Because of that cyano group, it stabilizes it quite a bit. Yeah, but in that case, you can just think of it as generic H-. All right, now let's continue on to carbohydrates. I had a handout up front for you guys. Did everybody grab a copy of that? If you don't, grab it on the way out. You guys need to have that memorized for the exam. I'm kidding. No, the naming of carbohydrates does not follow the normal IUPAC naming, but it's IUPAC accepted and allowed. It's really, really tough to remember all of the carbohydrates. I leave that for the biochemists to worry about. But we will get into a little bit of naming as far as carbohydrates goes. The big thing with carbohydrates is this reaction. You guys have seen this probably all the way since you were in like 5th grade.
I've never seen that in my life.
So back in your very, very first biology class. So what do we call this reaction? Photosynthesis, right? So it's the mechanism through which our planet produces almost all of its energy, right? We capture sunlight and we store the energy from sunlight in carbohydrates, primarily as deep glucose. It used to be the main paradigm for biology that this was how it was done. It wasn't until the kind of mid-1900s that we realized there are a lot of other metabolic pathways besides just photosynthesis and storing things as carbohydrates. We have even found forms of life where they don't need sunlight to operate at all, and that's pretty bizarre. But we're going to focus primarily on these types of carbohydrates. There are two main classes of carbohydrates, though. All right, so I'm going to draw two different molecules side by side. They're very similar to one another. This is going back to first term representation too. You guys remember this? Yes, Fischer Projections. So what's the deal with Fischer Projections? Yeah, so the horizontal part you can think of as bending backwards like a C, and then the vertical part bends backwards, the horizontal part bends out. So you can kind of think of this as a cat laying on its back with its arms up, right? The cat analogy. If you go on Mastering Organic Chemistry, they have good review on Fischer Projections, but you should be able to designate R and S. We're not going to spend time on that because we already have. When we number these, what we do is we number down the center. So we go 1, 2, 3, 4, 5. So the main carbon chain is obviously going to be some sort of pentane derivative. And then the other thing we look at is this top functional group. So we've got an aldehyde. And aldehydes are called aldols. Or aldo, sorry. So these are a little bit different. A lot of carbohydrates have these aldehydes on them, but some of them do not. So let's take a look at a different one. So we've got OH, 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 H, H, H. And then we've got CH2OH. All right, so if we number these, we've still got 1, 2, 3, 4, 5. In this case, we actually, I goofed. I was looking at the wrong molecule on my sheet. We do go 1, 2, 3, 4, 5, 6. Thank you. So if we were to look at this, this would be a hexane derivative. But instead of an aldehyde, we've now got a ketone derivative. And so we call these keto functional groups. So if we were to name these, what we call this first one would be an aldopentose. This is the parent name. However, we do have a couple different types of aldopentoses. So if you look at the sheet that I handed out to you guys, you can see the family tree of D-aldose. And we've got, which one would it be on here? What do you guys think? D-ribose. So if we go through our family tree, we can call this D-ribose. If we go and we name the other one, we would call this an ketohexose or ketohexose. I always say these wrong. And then if you go on the other side of your family tree, you've got a family tree of D-ketoses. And which one would this be? It's a tongue twister. I don't even know if I can say this. Be D-psychos. You can just mumble it if we can't pronounce it. But the ketohexoses are the parents simply because they have a ketone on top. The aldoses have the aldehyde on top. So there are two main groups of aldehydes, and this family tree will help guide you in terms of the specific designation. One thing you may notice on the family tree that I handed out is that this bottom right alcohol is always, always, always on the right. And so in particular, we call these D isomers. It's just the suffix for aldehydes. So like glucose, fructose, they always have the OSE. Or carbohydrates, excuse me. Thank you. So these are always to the right. When you draw the Fischer representation. Or sorry, yeah, Fischer representation. And this is going to be a D sugar. Do you guys remember me saying that they can actually make glucose with that flipped on the other side? And what was special about that glucose?
0 calories.
Yeah, 0 calories. So if this alcohol is on the other side, it doesn't get metabolized correctly, and they've actually looked at that for artificial sweeteners, but it's super, super expensive to make, about $100 a gram, so it's not practical in terms of trying to make Diet Coke or something like that. It does taste exactly the same, though. It's just too expensive to make. All right, I've got a trivia question for you guys now. How many isomers are there for each of these?
Number stereocenter.
Yeah, how do we figure out the number of isomers?
Oh, it's 2 power of number of.
Yeah, exactly. So in D-ribose there, in that family of pentoses, we have 3 stereocenters. So that'd be 2 to the n equals 8, right? Versus for the ketohexoses, we've got the same thing, 2 to the n equals 8. But if we look at our sheet, we only have 4 of them, and why is that? Yeah, exactly. So we could say only 4 are natural. You could theoretically make 8 different isomers, but 4 will only occur naturally on our planet, at least, that we are aware of. All right, so now let's go a little bit into some old chemistry. And this was actually based on a problem the day we did. Excuse me. Oh. Let me make this. There we go. What do you think happens if we take this molecule and add acid to it? What was that? It'll ring close, right? So if we were to go through and do this whole mechanism, we could ring close it. And what functional group is this? Yeah, it's a hemiacetal, right? It only added in once, so we call this a hemiacetal. And if this does seem pretty foreign to you, I would recommend going back to pod number 6. We've actually done the full mechanism for these already. But carbohydrates, as we saw in problem of the day number 6, like to cyclize and form hemiacetals. with their hemiacetal form. So let's take a look at glucose, and we're going to try representing it a few different ways. So let's draw a glucose first using a Fischer projection. So we've got CH2OH on the bottom. All of these carbohydrates have that CH2OH on the bottom. And then we've got an OH, H, OH, OH, H, H, OH, and H. So this is D-glucose. But we can actually cyclize D-glucose. And that was problem of the day 6. So I won't show the full mechanism. But we've got a few different ways of representing it. So I'll draw both of these. The first one is called the Haworth projection. And when we draw it this way, what we do is we kind of view this as an edge-on view for carbohydrates. So we've got one side of the ring kind of coming towards our eye, and then the back one going back like that. Let me try to clean this up a bit. And then we just draw vertical lines for all of the carbon positions. Then we go CH2OH. That means that one's sticking up. The other one sticking up is a hydrogen. Hydrogen. Got a hydrogen there and an OH there. Hydrogen. And OH. H. OH. And OH. So this would be the Haworth projection. I personally am not a big fan of these, but they show them in your book, so I wanted to show them to you guys. What's the preferred way to draw 6-membered rings?
Not like that.
Yeah, not like that. Chair conformation. I know you guys hate chair conformations, but they're the best way, I think, to actually represent carbohydrates. But these are equivalent ways of drawing them. So let's do the chair for this. All right, so we've got the chair conformation. Let's just really quickly do the other conformations. And then we'll address why we have two different possible products out of this. Yeah, these are a pain to draw. So that's the other Haworth representation, and then the other chair representation looks like this. Do that 10 times fast.
No.
All right, what's the difference between these? Yeah, just the OH group, right? So we could get either of these. And the only difference between these are these guys are in different positions, right? And so what we call these are alpha or beta carbohydrates. The alpha one corresponds to the axial position. So which one's axial, the left or the right pair? The left pair, right? So if we look at that OH group, it's axial. So this would be alpha D-glucose. This one would be beta D-glucose. And why are we getting a mixture of these?
Because the O backs flips instead of goes.
Yeah, exactly. So if we look at nucleophilic attack on an aldehyde, it can occur from either the top face or the bottom face, right? So we're going to actually get a mixture of products here. And we also have a new term that I want you guys to know because I'll be referring to it. If we look at this carbon here, this is a carbon where the stereocenters differ, right? And so what we call this is the anomeric carbon. So you notice how none of the other stereocenters changed? It was only that anomeric carbon. So it's always that carbon when you draw the chair conformation like this in the bottom right-hand corner. And that is what defines a alpha or beta carbohydrate. So let's make a list of terminology. Alpha equals axial at anomeric carbon. Beta equals equatorial at the anomeric carbon. And then the difference between these is only one stereocenter, and so what we call this is epimers. The other term I wanted to bring up was mutarotation. What do you guys think mutarotation refers to in terms of carbohydrates? Yeah. So this is kind of troubling for a lot of chemists because they go through all this trouble and they say, all right, I purified alpha D-glucose. I've got it completely clean. I have none of this beta D-glucose. I'm going to take this and I'm going to throw it in some water. What do you think is going to happen?
It's going to unwind and then...
It's going to unwind and then rewind up, and you'll get a 50-50 mixture again. So mutarotation refers to that ability to be in equilibrium in water and go in between that alpha and beta form. At the anomeric carbon. So mutarotation is usually in reference to carbohydrates when they close and then unwind and back and forth. All right, there's also two other terms. We'll get over this definition stuff here soon. The next term is pyranose. So a pyranose is a six-membered ring with oxygen. So if we looked at glucose, glucose would be an example of a pyranose ring because if we count the ring size, it's a six-membered ring. Sometimes we don't have carbohydrates that can form six-membered rings. What's the other preferred ring size? 5. So in that case, we run into furanoses. And these are 5-membered rings with oxygens. So it's more that they use that parent furan, and then they know it's a derivative of furan. It's not the same as furan because it's not aromatic, but they took that parent name and they're reusing it. Yeah, so pyran isn't aromatic, furan is aromatic, but they, in this case, just vary in their ring size. All right, does that make sense? A lot of new terminology for carbohydrates, and I just wanted to get that out of the way before we continue on. All right, so let's go into one reaction. This one will be nice because we already know it. And then we'll call it a day. So what do you think it means when I'm referring to a monosaccharide? It's only one sugar. So we can get into polysaccharides, which we'll cover later, but monosaccharides, we're just looking at single sugar units. And the first reaction we're going to see is acylation. Nice and easy one. And I'm going to draw this in the chair conformation because I prefer that. And we're going to react this with a special reagent. What's this called? Yeah, acetic anhydride. So it's an anhydride, in this case a derivative of acetic acid. And in this case, we like to abbreviate these as AC, just to cut down the amount of stuff we have to draw. So if you take acetic anhydride and you react it with D-glucose, what do you think is going to happen? Assume this is in excess too.
It's gonna put the AC on the.
You've got a super good electrophile. It wants nucleophiles. We've got 1, 2, 3, 4, 5 different nucleophiles. This will react with each one of those alcohols and install an acyl group on there.
Is there any way to isolate which impact?
Not very well. That's an interesting question, though, because you know how we've talked a little bit about protecting groups? Protecting groups for carbohydrates, oh my gosh, you could spend a lifetime studying that and still not be very good at it. There are ways to selectively protect these positions, but it gets into super, super advanced chemistry. So as far as we're concerned, we're just going to protect all of the alcohols with acylation. We're not going to selectively protect certain alcohols. We will see a reaction tomorrow where we can react the alcohol at the anomeric carbon, but we're not going to get there today. So we're going to stop with acylation today and then continue on into reactions more tomorrow. All right, remember, if you're in Tuesday lab, we have lab today. If you're in Monday lab, we have lab next week. I emailed you guys about the lab reports. Lab reports are condensed down, so make sure you check your email. You don't need to do the full lab report as listed in the lab handout. That way you guys can have some more time to study.